So this is from your book, Triola. The central limit theorem. In the preceding section, we saw that the sampling distribution of sample means tends to be normal distribution as the sample increases. In this section, we introduce and apply the central limit theorem. The central limit theorem allows us to use a normal distribution for some very meaningful and important applications. Given any population, with any distribution, whether it be uniform, skewed, whatever, and so we're talking about distributions that are not normal now, the distribution of sample means can be approximated by a normal distribution when the samples are large enough. There are some special cases of very non-normal distributions for which the requirement isn't quite enough, and that's just, you guys don't really need to deal with that because you're obviously only dealing with this kind of thing. So what are we doing? So now we have a situation where we might not be normal initially. So can we use what we know? Can we use normal distribution approximations to, and the methods that we know, we just learned normal CDF and inverse norm. Can we use that stuff to approximate things with these non-normal kind of distributions? So yes, if the sample size is greater than 30, and that's majority, right? We're not dealing with rare occasions, okay? We're dealing with your majority. The sampling distribution can be approximated by a normal distribution with mean of mu and standard deviation of sigma over the square root of n. So now what's happening is we're selecting a sample size. The sample size that we select must be greater than 30 to be able to use normal distribution approximations. So what that does is there's a slight change with your standard deviation, which means there's a slight change with your calculation of your z-score. So before, you guys saw a z-score represented as, let me actually go here. When I introduced z-scores, we had a normal distribution with a center, mean, right? And we had a standard normal distribution with the center 0, and these were z-scores, right? And I said, well, this is a normal distribution curve, this is a standard normal distribution curve, and if I want to standardize, let's say I have a data value here represented 1 standard deviation above the mean, the z-score for that would be 1, but how would I calculate that if I couldn't directly see it? What if it was in between the two? So how do I standardize these values if I have different types of means and standard deviations? I convert them to z-scores with this formula. Z is equal to, and you'll see the difference. So this is the formula we're using here. This is the formula we saw before, x minus mu over sigma. So how did I standardize them? I found its corresponding z-score. Now, if you guys are using tables rather than the calculator trick, you have to do that for every single data value and then go onto your tables to calculate whatever probability or given probability in order to use your inverse norm and such. In order to find area, or in order to find a corresponding data value to a z-score, you have to convert every single one. That's why the calculator trick makes it a lot faster. Here though, you see your z, if you can't see it, let me write it. Your z-score calculation is now x bar minus mu, excuse me, over sigma over the square root of n. Now has a little slight change to it, which your calculator doesn't necessarily automatically do, which means that you are going to have to go through this to standardize your situation so that you can use the methods that you're used to, such as normal CDF and inverse norm. But you're only going to do that if these conditions are met. So requirements, right? Population has a normal distribution, or the sample size that you're selecting is greater than 30. If either one of those conditions are met, then you can use your methods. If not, then you can't do this. It doesn't mean anything for your situation. So, for example, I'll do number 5. In exercises 5 through 8, blah, assume that females have pulse rates that are normally distributed. Okay, that's nice. They're normally distributed already. Okay, with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Based on blah, find A, So let's do number 5. If, I'll go ahead and use my purple again. If one adult is randomly selected, find the probability that her pulse rate is less than 80 beats per minute. I don't know if you recognize that before I was stressing, when I talked about these situations, when I did IQ scores, I always said, you know, finding the area was the same as finding the percentage, or also finding the probability. If I randomly select one and that probability or whatever, that value, that thing that I select is between these two. I always stressed one. I was only selecting one. So here I'm only selecting one. That goes along with what I'm used to. So, okay, I can actually go straight to my curve. This is a normal distribution curve, which is good. The center is 74, right? The mean, 74. So the center is 74. The standard deviation is 12.5 beats per minute, BPM. Find the probability that her pulse rate is less than 80 beats per minute. Here's 80, less is to the left. Find the area under the curve, right? Probability that this person had less than 80 beats per minute as their heart rate. How do I do that? I want area, normal CDF. My left bound is technically negative infinity, but what did we say to do? Use a large negative number. To move this over. My right bound is the rightmost portion of this curve, which is 80. I should put another 0 on it. And the mean was 74, and the standard deviation was 12.5. So right now, nothing is really changing. Okay, so let me look at my calculator real fast. That's why I'm kind of going through this a little bit faster, because we just did these kind of situations. So normal CDF, second bars, normal CDF, negative large number, upper was 80. The mean, I keep forgetting, 74, and then the standard deviation was 12.5. Okay, so this is not technically very different because I'm only selecting one. And so 68.4. Okay, rounded to the nearest tenth of a percent. So 68.4 approximately. 68.4% chance, okay, that if I only select one adult female, the probability that her pulse rate is less than 80 beats per minute is 68.4%. Okay, now, I went through that. It's just 5A. I went through that fast because it's no different than what we've been doing. What's going to change? B, 16 females are selected from this population. So now I'm not selecting one, I'm selecting 16. So now I have a sample size N. 16 are selected rather than 1. Find the probability that these pulse rates, that they have a mean less than 80 beats per minute. Find the probability that these pulse rates, these 16 that I selected, have a mean that is less than 80. So look, honestly, the picture is not going to really vary, right? It's going to still have, an area to the left. But first of all, can I use normal CDF? Am I allowed to? This is the Central Limit Theorem applied. Can I use normal CDF? Well, first of all, I'm not selecting more than 30, right? I have to select more than 30 if the population is not normally distributed. If the population is normally distributed, then I can select less than 30. Well, what does it tell me? Females have pulse rates that are normally distributed with a mean of 74 and a standard deviation of 12.5. So due to the fact that they had already had normally distributed situation from the population, I am allowed to go ahead and use my methods even though the sample size is less than 30, which actually already answered C. Why can the normal distribution be used in part B even though the sample size does not exceed 30? It can be used because I was already normally distributed. If this wasn't here, where it said it was skewed, or it was not normally distributed, or it didn't even say that, it had a normal distribution, it was just some distribution, then I would have to select a sample size that is greater than 30. And if I didn't select a sample size that was greater than 30, and if I wasn't normally distributed, then nothing I do matters, and I can't do anything. It's a waste of time, right? So that's what the central limit says. Central limit theorem says. You have to check to know if the population was already normally distributed, or check that the sample size that you select is bigger than 30. If it is, if either one of those scenarios are good, then you can go ahead and use the methods that we are used to. But you have a little extra work to do. You have to standardize this first. So before I go into normal CDF, I have to convert to an SND curve or to a z-score. What z-score corresponds to this? But the z-score that I choose, or the z-score that I find, where is it? Has to be found by using this formula. Okay? X bar, the mean, minus the population mean. Now I have to use this. Your calculator doesn't do this. So we have to standardize it first now before we can do normal CDF. I have to find the corresponding z-score. Don't forget, now I'm on a standard normal distribution curve. I have to find this corresponding value, right, that matches this location, but on a standard curve. But I have to calculate it using that formula, because now I'm selecting more than one. So the question asked, find the probability that they have pulse rates with a mean less than 80 beats per minute. This represents that X bar, right? Here it represented X, one data value. Here it's representing X bar because we're saying, does that little sample size have a mean that is less than 80? Because I can't represent all 16 of those values, so I have to find the mean of it. What does the mean represent, or does the mean have less than 80 beats per minute? Does their average have less than 80 beats per minute? So 80 minus mu, what was my population mean here? 74 divided by my standard deviation, which was 12.5. And then that divided by the square root of my sample size, 16. Calculate that first before I do anything else. And then I can go and use what we're used to, my normal CDF, to find that average. So, all right, so, you could plug it all in. You just have to be very careful of your order of operations. I'll show you like that. So if you're going to just plug it all directly in, parentheses around the numerator, 80 minus 74, right? That's my numerator. Yep. Divided by my full denominator, which is 12.5, divided by the square root of 16. I'm just assuming that, we don't have easy numbers, right? Close. So I'm saying this divided by this. Now, if you have an 83, I think they also have parentheses around the square root, so you might have a double parenthesis here just to close the square root and then to close the denominator. What you should get is 1.92. So make sure you go through that and check that you do the proper order of operations to find 1.92. Okay, so the corresponding z-score to that value 80, which represents the mean of those 16, is 1.92. Now that's not the answer to my question, because the question asked find the probability that they had a mean less than 80. So now I could use normal CDF. And find this area. A large negative number, rightmost. And then, my mean is 0, my standard deviation is 1 because I'm on a standard curve. I'm from here. I'm finding this area. This area is the same as this area. So if I calculate it here, I calculate it there. But I had to standardize it first. So I had to go through this process first. So this was 1.92. Actually, it was exactly 1.92. So let me actually do that. You guys see what it is. Second bars, normal CDF, large negative number, Upper number was, excuse me, 1.92. And then my mean is 0, my standard deviation is 1, because I'm back to a normal distribution curve, a standard normal distribution curve. Don't forget that. You converted it. 97.3%. So approximately 0.9725, 0.973, or 97.3%. Which makes sense, right? I would imagine it would be a large percentage. You know, I'm to the right of the center, so it should be greater than 50%. You know, make sure the percent makes sense to your situation. So again, if I'm selecting 1, that's fine. I use the same stuff that I'm used to. But if I'm selecting more than 1, now the central limit theorem applies, and that group has to be greater than 30, right? Has to be greater than 30 if I'm not already normally distributed. If I'm already normally distributed, I can select any sample I want, which is why 16 was okay. Other than that, this has to be greater than 30. But now that I'm selecting more than 1, I have to go through this extra step where now I have to standardize my situation using a little slight change to that z-score formula that we're used to, and then deal with that to find the corresponding area.